So let me introduce you. Hi everyone, for the last installment of the NLG seminar this semester, today we have Jinchi Lv. Jinchi is a Kenneth King Stonier Chair in Business Administration, Department Chair, Professor in Data Sciences and Operations Department of the Marshall School of Business at the University of Southern California, and Professor in the Department of Mathematics at USC. He received his PhD in Mathematics from Princeton University in 2007. He was McAllister Associate Professor in Business Administration at USC from 2016 to 2019. His research interests include statistics, data science, artificial intelligence, machine learning, and business applications, as well as blockchain and large language models. His papers have been published in journals in statistics, economics, business, computer science, information theory, neuroscience, and biology.
Thank you, Jinchi, for the very kind introduction, and I want to thank John for kind of the invitation. It's lovely to come to this nice part of the town, and I know USC has one of the famous ISI Institute, right? So I did Marina Del Rey, and I think I walked around years ago, but didn't realize actually this institute is so close to the bay, right? So it's lovely, and also very enjoyed the group meeting, and it's translated developments. So the agent actually is very powerful, right? So on the other hand, if you have like a system agent, sometimes it's more interesting. For example, you can learn the behavior of one single agent, right? Multiple agents, and try to be more adaptive, right? Yeah. So today, actually, I want to share with people here a line research. Actually, my collaborators and I have started working on this very recently. As you can imagine, there's a LLM in the title, right? Which means can never happen before 2022, right? For a good reason. And this is joint work with Yingying Fan, a faculty at the USC Marshall. And also is a postdoc in my group, and Yurou actually visiting student. So the title is actually so-called, it's about time series prediction and inference by leveraging large language model. So I'll discuss basically the motivation, the idea, inspiration, and also share with some case study. It's also good to have like introductory comments and discussions. So as we know, large language model actually being heavily used in all aspects, right? For example, in everyday life, and if you want to, sometimes in old days, you Google search, right? And these days, actually, if you say, oh, I'm not feeling well, and maybe I got a cold, right? Between different things, and you may want to ask LLM, right? And get ideas. So, and also in scientific research, actually, is also being used in other disciplines. For example, scientists are trying to use AI tools, develop new protein structures, right? And for medical purpose. And for me, actually, we know that this language model, right, which means it's based on transformer model and the advanced version. So naturally, it's actually advanced tools for understanding what we speak every day, right? And communication, the writing. So here, at least, basically, for me, actually, I'm interested in two particular tasks for natural language process. One is a summary. Imagine if you love reading, right? For example, the Pride and Prejudice, right? It's a beautiful novel. On the other hand, if you want to summarize the whole novel into a short summary, right? For example, if you only have budget of say 200 words, right? Or 500 words or 1,000 words, as a human writer, you want to decide what to put in the first paragraph, right? Second paragraph. Of course, in your mind, you need to understand the main characters, main plots, right? The storyline. But for machines, actually can need write, for example, like intelligent summaries. Second one is actually closer to my research field, actually, so-called what can you make out of the data, right? For example, you have tons of data, what's numerical, text, or audio images, right? How can you make a best forecast and prediction? So speak of, for example, summary. So of course, LLM summary is very good tool for large text reduction, right? For example, if a 100-page document, if you trust AI, you can ask LLM to give you a summary, right? 1 page or half page, right? The big question is, what about the quality of the final summary? Which means, plus actually the another complication is even your same prompt, right? For example, you work with your favorite LLM tools and use the same prompt, repeat it twice, you get different answers. And by design, that is because the randomly injected in the model output, right? So actually, in statistical field, randomness actually is fundamental. On one hand, you can argue, give you uncertainty, right? Which means all of us, if you work with same model, we get different answers, right? On the other hand, if you think about the history of human evolution, right? Randomness is actually not a bad thing, right? Because suddenly there's random ideas and the creation of different mutations, our genetic, basically the traits, and also, sometimes you can have like disrupt ideas, right? For example, invention of like AC, and also invention of, for example, like general relativity theory, right? This is actually not a conventional thinking. So the one question would be in my research group is, if you look at different LLM summaries, whether it's same LLM tool or different LLM tools, right? How to compare different summaries, say which maybe version A is better than version B, right? So the approach actually we did is actually we look at question, actually we design an inference tool. By inference means, well, if you have, for example, original text, right? For example, like maybe a 10-page text, right? And summary could be half a page. You want to have a metric for comparing, for mapping the summary to the main text, which means that even if you only have a half-page budget, right? You hopefully can basically you can extract the most important key points, right? For example, imagine if you write any paper, you have the selling points, right? If you write imagine if you write summary, if you forget about selling points, of course, it's not a good summary, right? So we leverage basically the BERT embeddings, for example, for the text, because you have the words embedding and also context positional. So BERT embedding we took as an input. So we use a tool, something called SVD, which is heavily used in auto problems, right? For example, if you think about over 10 years back, the famous Netflix prize, right? If you have like missing entries, how can you impute and guess all our preferences, right? Turns out one fundamental tool, something called SVD, single value decomposition. So we took the BERT embedding for the different words and tokens and work with the latest SVD idea. Long story short, we came up with algorithms called LIDS, LIDS. Actually, is if you're interested in this one, actually you can go to just Google search and find the archive paper. And give you the idea, essentially, we introduced the metric for comparing the text to summaries. Of course, higher number means is better quality, right? And also we can understand the uncertainty. For example, you can use, for example, any of favorite element tools, right? With GPT or Gemini, right? So our output is different. So you understand if you use your favorite tool, what is intrinsic uncertainty, right? And second, the quality. And another point, actually, we were very interested in is, just imagine if you like hiking, right? If you look at a mountain, of course, from distance, you only see the outline, right? You can see the shape of the mountain. But when you walk closer, gradually you can see more and more details, right? Maybe somewhere you see hikers and the building, or like not buildings, like pavilions, right? Whatever, right? Or temples, right? Same thing for text, right? Imagine, so if you have like a summary of a huge text, right? So how can you visualize the text in a natural way? Meaning that maybe if you, for example, from 3,000 foot, right? Like you want to see, for example, like the major point of the text, right? The most important aspect, right? We walk closer, meaning that you have more budget. Now have basically second paragraph, right? What should I put there? So essentially, our tool provides a layered view of text, meaning that for the first layer tells you, oh, the most important topic actually should be this theme. And when you think about theme, actually should be carried by words, right? Because we always see the words every day, right? But if you put in different ways, different combinations, give you different meanings. And also we make our layered keyword selection like reproducible, meaning that even if you repeat the exercise again, for example, with different outputs from LLM with repeated prompt, actually the result should be stable. Statistically, something so-called error, basically the selection with error control, meaning that when you and I basically doing an experiment, we want to control the error rate. When it's not at all, when we do separate experiments, our results will be hugely different, right? So same thing for like for any language outputs, you want to make sure this high quality. But today, actually, I want to switch a little bit. I want to focus more on the second problem. How can we do more accurate forecasting and prediction by leveraging large amount of text? I'll give you some examples, right? But again, for I know that this LLM summary is more related to the research group here because about language modeling. If you're interested in it, we can like chat offline. So the central question our research team are trying to ask is how can turn large amount of information, text information, which is available freely and openly, right, online and in different locations, and we can turn that information into a more powerful tool for inference, meaning that we want to forecast something, say for tomorrow, not only have a single number, right, and also you have intervals in that is credible, is region, right? And in particular, in my talk, actually, in our research project, actually, we focus on something called inflation forecast, right, which is so central to our daily lives, right? Imagine if you go to Trader Joe's, right? If you want to buy the X, when you realize the price went up, right? Or if you go to Starbucks, you want to get a coffee, suddenly you need to pay more, right? Meaning that things are happening, maybe the price going up, inflation is on the rise, right? Yeah. Okay, so that is the background of the problem. So actually, our research actually is actually beyond the inflation forecasting. So one particular application could be how do we forecast general macroeconomic indicators? For example, if you think about US, right? So lots of very important economic indicators. For example, could it be GDP? Could it be interest rate? Lots of discussions about Federal Reserve, right? Whether it should keep cutting rates or should it be start rebound, right? Looks like maybe given what's happening now, I heard from radio, right? Says policy would be they cannot further lower the rates, right? At one point they need to go the other direction, right? So of course, once you do that, things will change. And actually, in terms of, for example, like inflation forecasting for not only US but around the globe, right? The global inflation forecast, according to IMF and also like Reuters, actually the regional forecast for next 2 or 3 years is actually so optimistic. Actually, for example, in 2025, as like a forecast to be 4.1%. Gradually, it will go down. Of course, that is the right trend, right? But on the other hand, any prediction can only be one possibility to influence many universes, right? Which means in next 2 or 3 years, anything can happen. Which means that even though if everything works well, it should be on the basically should be dropping. But on the other hand, sometimes it will be changing in linear fashion, right? Sometimes you can rebound, right? So actually, from the this is already April, right? Last month, actually, IMF actually warned that if energy price, for example, if you go for example, like add a gas to a car, right? If the price keeps going up, like then it's going to affect the inflation and also lower the global global growth, right? A rule of thumb is if I notice actually the gas price here, so it's actually close to 7, which is of course is increment, right? Increase, right? So the rule of thumb is whenever there is like a sustained period of 10% rise in energy price, it roughly translates into 40 basis points in global inflation. Well, meaning that you add 0.4%, and it's actually it's a lot of like cascading effects, right? Okay, I'm going to explain how the governments actually are forecasting this, for example, like inflation in an official way, right? On the other hand, we need like signal that is like timely, meaning that because the typical way of doing forecasting of inflation is, every month the different countries, right? They have different economic experts, right? They have pool experts. They do surveys and try to get the basically the policies of the economy, right? What's happening, meaning that at the end of the month, they collect basic bill data, right? They aggregate them together. It's probably something called CPI inflation for 1 month, right? This is, for example, for March, you can do the same thing, right? For April, because today is April 7th, right? Meaning that you have to wait for a while to get the official data, right? On the other hand, inflation is around us every day, right? You go shopping and you feel basically what's changing, right? Meaning that how can we leverage the real-time information or high-frequency information for more accurate and forecasting for CPI, not just like one number per month, right? You want to have, for example, maybe every day, like today, April 7th, tomorrow, April 8th, right? How can we do that? So forecasting actually is a classical problem in time series literature, economics and finance, because all the fact forecasts, right? For example, what's happening for next month or next like a quarter or next year is going to impact how basically the government, different government agencies share the policy, right? For example, monetary policy, labor markets, for example, interest rate, right? What happens to the mortgage, right? When people buying houses, of course, going to affect everything, not to mention financial markets. As I mentioned, the classical way of forecasting or reporting inflation is rely on the low frequency, which is monthly, and survey-based indicators. On one hand, they argue that this is gold standard, right? Because they had real experts, kind of field data is aggregated, is official number. On the other hand, it's very slow, right?
Sorry.
Yep.
So I'm not at all knowledgeable about any of this. So who's getting asked the survey and what are the questions they're being asked?
So essentially depends on different countries how to do that, right? So usually they have pool, for example, like leading like economists, right? So they have the pool experts and the pool, they basically you can say, oh, for last month, right? How do you feel about for example, like the price movement because the different segments, right? In the end, they put information together, they get so-called the aggregate information. Yeah.
So like if you want to know by a survey about whether they're like how inflation is doing, you ask an economist how was inflation doing?
So essentially they rely on the experts to collect the field data.
Okay, but you don't ask somebody like how much did bread cost at this store?
No, it's not the case, right? So imagine, for example, on the other hand, you argue that inflation is actually around everyday life, right? If you buy bread or egg or milk, right? Or even get like a coffee, right? If the prices keep fluctuating, actually, this is a real thing, right? Yeah. So on the other hand, if you do that, I can imagine the government will be super loaded, right? So if you ask, for example, interview people, right? So yeah.
Okay.
Is the field data published or?
It's published essentially. So all the countries, for example, like US, China, all the countries, right? So they regularly publish this number because this number is very important. It's more like it's more like something you once the public number, you can see what's happening in the next like 2 or 3 months, right? Or half a year, you can make adjustments, right? Yeah. Or people say, oh, maybe the interest rate is going to go up or go down, right? Yeah, because interest rate, unemployment, and also inflation, they're all interrelated. Yeah, yeah.
What is the nature of the field data itself? Like, is this data that you could proactively collect before the report is released, or?
So there's different government agencies, for example, like usually they have the survey agency to conduct the surveys. In the end, they aggregate everything, they publish the official number, right? Yeah.
So it'd be like whether or not the weather in Florida affected orange juice crops for this month. That's the kind of thing that gets published.
Well, that could be different surveys, right? Yeah, could be, yeah. On the other hand, so essentially for inflation, there's different keywords, right? For example, could be essentially it's aggregation of everything, right? For example, like yeah. So essentially, for example, if you want to understand the for example, like CPI data for all the countries or World Bank, right? You can download data. It's the official number. On the other hand, it's very low frequency. It's monthly data. So if you think about 10-year period, right? We only get like 120 points. And now rely on the past 10 years, you want to predict next month, which means your training data is only 120 points. You want to predict next month. It's not easy. On the other hand, it's highly noisy, right? Yeah. Whatever you do is going to most likely deviate from the truth, right? What's happening in next month, right? On the other hand, as for example, just mentioned, right? You can, if you talk to your family members, right, or friends around you, say, how do you feel about like for example, the consumer, like the behavior and the prices, right? You can get a sense, right? For example, particularly in Los Angeles, whether its price is going up or going down, right? Or if we go to different parts of the country, right? There's different moments and also different sectors, right? So On the other hand, we have online text, right? Just imagine if you go to Starbucks and today you need to pay more. What you can do is you call your phone, right? And you go to any of like favorite site. You can say, I leave a comment, right? I bought a coffee today, actually in Marina Del Rey, and turns out it cost more, right? So everyone can do that, which means that it's high frequency. You don't need to wait for like 1 month, right? Any moment of the day, and each of us can do that, and also can do this in Los Angeles and Florida, New York, all the different places, right? So we have lots of information, high frequency, but on the other hand, it's very noisy, right? So it depends on which region you're looking at, right? For example, imagine Los Angeles, of course, could be more costly, right, than on other parts, right? And also it depends on who are reporting. So it's very noisy. So for our team, actually, we're thinking about the following questions, right? So we want to leverage the developments in large language model, right? Just imagine if you have a social media web, like a posts, right? So we have tons of posts every day, and maybe we can ask, for example, LLM to trying to make sense of the post, the text, right? Say whether is any information there reflecting the economic, for example, activity, right? For example, it's reflecting the price movement. We need to extract information and trying to provide, for example, level, right? So actually for us, essentially we introduce continuous like a range. 1 means absolute inflation. 0 means absolute deflation. 0.5 means, well, nothing's happening, right? It's not, yeah, it's not too pricey or yeah, it's somewhere in the middle, right? But the question is, we have 2 words, right? One is the gold standard, low frequency, high quality official data. The other one is, low quality because very noisy information, but high frequency, abundant information from text. How can we combine the 2 for doing the forecasting problem? Okay, so particularly for this project, we're trying to focus on statistical problem. Imagine capital T represents today. So standing today, actually, of course, we have information from the whole history, right? For example, the past 10 years, we want to predict our target. Why you can think of this as, for example, what is the CPI and inflation each month ahead, right? For example, in 3 months, we want to predict the inflation for 3 months from today. But in practice, of course, we provide a range, right? Because any number you guess may not be accurate, right? So we want to have a good coverage, meaning that maybe on average, our interval actually choose the future observed value by a high probability, for example, 95% probability, right? If you think of the problem, one simple way of designing the prediction interval is to make it as wide as possible, right? Meaning that what's weather tomorrow could be anywhere between sunny to snowing, right? And then if you do that, of course, give you good coverage, but not too meaningful, right? Because in Los Angeles, I've been here for many years. I don't recall that it ever snowed, right? But it's interesting, in recent 2 years, if you look at the mountain, right? Sometimes in winter, you can see the white tops, right? So the point is, you want to have good coverage. On the other hand, you want to make the interval as short as possible, right? That means you have basically a very tight prediction. Okay, as I mentioned at the beginning of the presentation, in this project, actually, we focus on problems so-called CPI prediction related to consumer price index, related to the inflation. And the classical methods actually rely on the ZT. ZT, for example, should be like survey-based official macro indicators. For example, in this literature, econ literature, the classical Z variable would be unemployment rate, right? So when the economy is doing great, what do you mean? Everyone's getting a job, right? Of course, unemployment rate will be lower. On the other hand, will be the opposite, right? We start with the baseline model, something like structural econometric models for forecasting the inflation, and particularly there is something called Phillips curve, which is inverse relationship between the unemployment rate and inflation. Yeah.
Sorry, so we're predicting CPI,
yeah,
which is a scalar. Right?
Yeah, scalar. Right?
And the input is the vector ZT, right?
Oh, actually, this is only this is actually only part of input. Yeah.
Okay, but it is a component of the input.
Yes, right.
And the D it's a reasonably small D, like
yes, right. Right. For example, in economic literature, actually, if you like, you use D equal to 1, meaning that you use, for example, unemployment rate, a single variable.
CPI. Sure.
Yeah, because economists love doing that because they argue which variable is the most powerful, right? So D could be 1, for example, could be unemployment rate, or if you like, make it 2, for example, like interest rate, right, and so forth, right? But of course, if you do that, it's highly unreliable, right? You only single variable, yes.
So in your variables, do you include the previous period CPI, or is that like a different?
Yes, actually, it's my next explanation is connected to what both of you just mentioned, right? On one hand, 102 may not be big enough, right? It's highly volatile. On the other hand, why don't you use a history, right? Yeah. This is basically the benchmark method. Something called AR means autoregressive, meaning that if you want to predict a basic CPI for next month, right? So we can use our history, for example, the CPI from the current month, the previous month, right? So you can go back to history. So you're using your own history for prediction, number one. Number two, you can also use some other economic indicators like unemployment rate for the prediction, right? Meaning that you have different information together, right? So this is classic of something called basically the Gordon triangle model in economics, using AR, your own history, and also plus unemployment rate. Yeah. Okay, before I present the formal algorithm and the details, let's take a look at the forecasting by the classical, the baseline methods, right? So essentially the gray curve here represents the movement of CPI month by month. And you can see it's quite wiggly, right? It's not like CPI is actually flat, right? It's pretty wiggly. And the reason why it's so wiggly because essentially it's essentially the monthly data. And there could be different changes, right? And if you look at 2020, of course, we know what happened, right? So things are basically, it's pretty big swing here, right? Up and downs. Okay, imagine we stand around here. This is probably the October of 2022. It's more like fall 2022, right? You stand around here. You want to do forecasting for CPI inflation for next year or so. What you can do, of course, you can rely on history, right? Which means the gray curve you observed. That's basically the AR model. You are using your own history, or you can talk to the economist, right? You can say, oh, maybe unemployment rate is so important, right? You add X. X means exogenous variables, right? But the thing is, this is basically the second part of the gray curve, this actual CPIs. Again, it's quite wiggly, right? If you think about two benchmark methods, AR and ARX, so one is a light blue, the other one is a blue curves, right? Both curves are pretty smooth, right? It's pretty smooth. And if you look at the interval here, so at each month you have interval, right? Sometimes shorter, sometimes longer. But if you look at the blue basic regions, they're pretty wide, meaning that classical methods, they essentially the intervals it's not too useful, right? It's more like tomorrow what's going to happen to the stock market movement, right? You can say, oh, anywhere between 100% to negative 100%, right? I mean, anything can happen, right? So this is actually the challenge for the reason I mentioned, right? Even if you rely on 10-year data, 12 times 10 is quite a small number, right? No wonder it's pretty wide range. But on the other hand, if you talk to friends around you, you might think what's happening today and yesterday, right? So this is actually the red curve is from our paper, something called LLM-TS. I'm going to explain what it means in a second. So the red curve actually a prediction based on LLM methods. Actually, you can see it's actually now a switching color, right? So the actual CPI curve is the black curve. You see the red curve, of course, is not perfectly matching the blue curve, right? Because no forecast actually is perfect, right? Because any model you basically pose could be wrong. On the other hand, if you look at the prediction intervals given by the new method, basically the red region, is actually narrower than the blue region, right? Meaning that the forecast actually is more meaningful because tighter. On the other hand, you see that you can capture overall trend, right? Not in a perfect way. And this is actually my favorite plot. Because for prediction, you can look at the distribution, right? For example, for next year or so, you can look at distribution. So the black curve here represents the future prediction distribution. Say, what does the inflation look like in the next 2 years also, right? Because of course they're random, right? You can look at distribution, the black curve. But if you look at the prediction by the classical methods, the two blue curves, light blue and blue curves. First, they are off, right? Meaning that the prediction curves center around 0, but actually the real CPI is not centered around 0. Second one is spread is also different. So on the other hand, the red curve is given by the LLM-based algorithm. So it actually is give you much better prediction of the future. Yeah.
How different is this AR and ARX from the random guess? Because like for me this is very similar to the random distribution.
Yeah.
How different are they from the distribution?
Yeah, it's a very good question, right? So it's because if you look at this one, it's not performing very well, right? Because problem is difficult to start with. So short answer is I'm going to mention some numbers. It's pretty close. It is pretty close. So actually, it's interesting according to economic literature because data is so limited, right? So actually, the most powerful method is something so-called just do the for example like a simple average, and essentially it's pretty close. And also for the random walk, this idea so actually it's also very close. Yeah. The margin not too big between the classical methods and the method you mentioned. Yeah.
And the LLM-TS, the input to LLM-TS model has this extra information from the the social.
Yes, right. Yeah. I would say a lot more information. Yeah.
And you're saying that that information makes this prediction better.
Yes, right. And precisely getting back to what John mentioned, right? If you talk to your friend, you can say, oh, maybe basically the bread costs more, right? You need to pay more money, right? Which means that inflation is actually is happening. Yeah.
In the prediction zone, does the predicted point have the true information about the previous data points in the predicted zone? You know what I mean? So like, okay, so for sure you have all the information up through 2022.
I know. Yeah, like October.
But then, like when you're predicting like in the later third, do you have the information? No, the later third.
Yeah.
Do you have information about the earlier third of that zone?
Oh, very good question, right? You can do either way. For example,
what are you doing?
Yeah, right. Yeah, probably can guess what I'm trying to say, right? So essentially, or you can use only purely the historical information, right? You pretend that you don't know anything. For example, even stand here, right? But on the other hand, in like economic forecasting, actually, it's good to have a moving window. We mean that a year from today, you already have more information, right? You can keep updating. Yeah.
So what is this?
So essentially, this is essentially, for example, if you look at this point, right? Because you already had. By the way, let me clarify. When we create this curve, so essentially, we're not peeking into the future, say what's going to happen, for example, 1 year from today, right? But since we are doing prediction,
the whole past.
Yes, right. It's more like you have trajectory of prediction. You can keep using your.
Was that true in the last slide?
Yes, right. So for example, benchmark method essentially is also moving window. For example, if we have prediction for next month, for the month after, of course, you can use your earlier prediction.
Right.
Yeah.
So I'm surprised then, because you have that little region of a big divergence at the beginning.
Yeah.
Since
you mean here, right?
There, right? Like you would think that once it goes up, right? Like you would start to predict up.
Yeah.
So what happened?
Yeah. So this is actually quite a this is actually something I also want to let me see. So let me see. This is actually which year is end of 20. Yeah. So actually, there's I think in the paper we mentioned some like usually some like important world events associated with different, for example, like this is actually the beginning of the pandemic, right? So this also might be happening, what's happening in that year. Sometimes could it be the conflict even different? Yeah, so this is could be the reason. Actually, this is the spike, the actual spike, right? Which means it's difficult problem because it's not easy to capture this one. On the other hand, maybe one argument would be because having to be that big spike in for example in 6 months, right? But since we're leveraging text information starting from here, meaning that the signal there, but not strong enough, and then later on actually can capture well. Yeah. But in general, it's very technical problem, right? Yeah. So basically, this is the question we are trying to ask ourselves. First one is how to turn the large amount of text into useful information, basically the surrogates for the inflation by using the LLMs. Second one is how to fuse the two components, right? One is field data, high quality. The other one is LLM derived the signals. It's high frequency, but it's very noisy because it can jump around. So this is the question we're trying to address in this project. So actually in the paper recently, by the way, if you go to archive, there's early version. Actually, we finished a significant review of the paper. In the end, I'm going to mention the more studies. Essentially, we look at the CPIs across basically 2 countries, one US and one China, and also we look at lots of macroeconomic variables. But during the talk, I'm going to focus on the CPI data from China. So the text data we use actually from the very popular social media site, Weibo from China, and meaning that if you have some comment about everyday life, you can just put it up any moment, right? For example, here this will be translation from one post. It's actually saying that maybe it's maybe toward the end of the pandemic, it's saying that actually the inflation pressure is very high. Ordinary people are not willing to consume, right? So probably we can remember around that period, right? Because we were confined at home. Not that they have no money. Once the economy restarts strongly, capital may again pour into real estate or even stocks, right? So this is also what's happening in US, right? For example, when the pandemic essentially eased, essentially all the consumption will go back, and also the economy. That's why in inflation actually there's more pressure during the period. So this is actually 2 data words I was alluding to at the beginning of my talk. So on one hand, we have government release data, right? So every month we have high quality indicated for one particular aspect of the economy. It's very low frequency. On the other hand, we have lots of discussions and posts on news articles online, and want to basically combine these 2 into a single framework. So now it's more like a thought process, right? What can you do? First, no-brainer idea would be, because people are saying that LLM is so powerful, right? It can develop agents, it can do this, right? I think the open cloud meaning that even during sleep, right, it can work for you. So one simple idea is, why don't we just use LLM to predict directly, right? Just go to basically the tool and ask, give a number for inflation next month, right? Of course, it can give you a number based on the text. So there's some limitations, or lots of limitations. Number one, so essentially it's like not like a white box model, right? You know what's happening. So it's a black box prediction, and as can it can be biased, right? Meaning that it's highly random and depends on what the input, right? Imagine if you write a post and you feed it into LLM, of course it can give you a number, right? If you use different text, you get a different number. So actually here I'm showing you our LLM-generated inflation index. I'm going to explain how this is constructed. But anyway, so every day I have to do a lot of data crunching, and you can calculate the number, say the daily index, right? So the blue curve. By the way, the red circles represent the actual CPI data, this monthly. If you look at the blue curve generated by the machine, actually it's pretty noisy, right? And it's weekly. Of course, you can see overall our grassroots discussions reflect the economic moment, right? For example, like the inflation. On the other hand, sometimes when inflation is going up, actually in this here is going down, right? It's mismatch. So meaning that the LLM outputs could be highly noisy. So here's basically the concept for our solution. So essentially, if you work with the feature data, which is monthly, this is structural model from economics, for example, ARX, meaning that you regress you're using history for prediction. X means it's the extension variable, like unemployment rate. You do this fitting. On the other hand, with lots of posts or news articles, what you can do is you can work with, for example, like GPT and BERT, trying to get embeddings of the text, which is like classical in NLP, right? And also, we can also generate LLM surrogate. I'm going to explain how to do this one, meaning that you can turn the text into numbers you can use, say, some proxies of the inflation for each given day. And the question is, how to combine the two? So I think for this part is a little bit interesting. Just imagine if you have two tools or two models, the conventional thinking would be, if you link the two models, usually the first idea you think of is maybe trying to draw links between the two models in terms of parameter sharing, right? Which is quite natural. But one nice surprise in the project is when trying to link two models, don't ask them to share parameters. On the other hand, the key idea is we can couple the errors, meaning that there's basically the residual here and residual here. We're trying to link the dependency between errors, not actually in the model parameters. And actually, you may think that is counterintuitive. On the other hand, this is the key, because if you're trying to link the two parameters, it could be bias you, because we have no idea how GPT is working, right? Because you don't have the actual model structure to open structure to work with. So here's basically the LLM-TS flowchart. So for the text data, just imagine if you look at the post information, right? Some could be about CPI and inflation. Some could be about general AI or any topic, right? So the pipeline actually we feed this post into transformer-based models and then give you economic narrative about what's happening, right? So can construct the surrogate, meaning that maybe today all of us, we just go online, any site, right? We can post information about how you feel about the prices. At the end of the day, we can put all the information together. We can turn our text short posts into a single number surrogate for the CPI today. You can do this day by day, right? This is one piece of information. On the other hand, if you work with, for example, like topic models, for example, if you have a text information, you can use something like a LDA, right? Latent derivative allocation model, trying to get what are the keywords, key topics, right, from the words, because this model is actually more interpretable. So our framework leverage both basic like BERT models and GPT annotations, and also classical LDA models for topic modeling. In the end, we're trying to piece the two together, doing a joint modeling for the actual CPI and also the surrogates constructed by the LLM tools. Okay, so if you love, for example, a little bit of mathematical definition on the model, so this is a classical model, the baseline model in for inflation forecasting in economics, right? YT would be inflation for today. What you can do is you look at the history, right? The last month, the previous 2 months for prediction, and ZT is more like for example, unemployment rate, something you can use for prediction. X actually is test embeddings. For example, for our posts, we embed as vectors, we're trying to prediction. So this is the target model. On the other hand, by using LLMs, we can turn all the posts into lots of pairs. For example, surrogates means what is proxy to CPI, say today and tomorrow, because now we have all the text information day by day, right? And also we can do text embeddings because we put in information today and tomorrow. In the end, we can get the embedding part. So this is quite interesting because so everything here is generated by the AI models, right? Surrogates. So YTS meaning that this is basically LLM generated CPI for today. And how do you predict this one? This classical model is so-called a V-vector autoregression model with exogenous variables. Again, you are using the history of the previous surrogates, right? That is history because you lack the variables. And also you look at the embedding of the text. So it's basically embedding best. So, and here you may be pondering, well, how do you know AI generates the signals, right? Because it's a black box model. So which means the model here could be totally wrong, which I agree. But on the other hand, so the interesting in project is we don't link the model parameters because this could be wrong. The only thing we link the error terms through the dependency, which means we don't know how AI works. This parametric model could be wrong, but this is actually a lot of more information here, and it actually makes more robust.
Sorry,
oh.
on the last slide, you have a acronym at the end. I didn't understand. DGP?
Oh, this is a data generating process.
Okay.
Yeah. So it's because we don't know how the, for example, like GPT and BERT models doing prediction, right? Because highly sophisticated, right? Yeah.
So here you said the next slide you want to model the noise.
Oh yes, right. Yeah, yeah.
Why you want to do that?
Yeah. Okay. So on one hand, we don't know how AI works, right? For example, how GPT turns the post into some proxies, right? On the other hand, we wrote the text, right? For example, if you go to Starbucks, you pay more for coffee, right? That means it's reflecting the CPI movements, right? So which means even if the basically the parametric structure could be wrong, but turns out it has a lot of information about inflation, right? That's why basically error terms, they should be correlated. One is from the government release data. The other one is basically AI generated. Yeah. Does that make sense?
So you're saying the error rates coming from the first module versus the second module should be correlated?
Should be correlated because they're trying to reflect the same thing about inflation. Yeah. It's like everyday activities around us. Yeah.
Are we training models in these pipelines, or are we just taking them as is? Like, for example, are we making it so that the errors are correlated by training the models to have the same error?
Oh, no. So we just leverage, because this is more like just imagine you have two separate models, right? And you do this one, actually, next slide, I'm going to show you empirically, they do share dependency. It's not like our mathematical assumption yet.
So we're taking the models as is and seeing that they're correlated.
Yes, right. Okay. Yeah. So then we leverage this one, because once you see the correlation, that means something information you can leverage on, right? Yeah. Yeah.
I can see how the predicted values should be correlated.
Yeah.
But why the errors should be correlated?
Oh, the reason is, generally speaking, the two pieces of information should be correlated, right? But on the other hand, any model used, for example, if you go to the model, right? Because just imagine this model could be wrong because essentially it's a linear model, right? Yeah. Which means we write this model, definitely there's lots of left information that cannot be explained here. And the second, the model could be different from the true BERT model, because this is a linear model, right? And we know the AI model can really be truly linear, right? Yeah. Yeah. So, yeah.
I was listening online and then I came in person. Okay. I don't know if I missed it, but so I don't understand what what are you doing with LLM? What's the actual data that you're looking at?
Yeah, actually,
how do you compute the
did not miss anything. So I'm going to explain a little bit about the data pipeline in a second, right?
Okay.
Yeah.
I'll wait.
But getting to your question, essentially, next slide, I'm going to show you the correlation, right? But I want to explain a little bit to intuition here. So this is the error term from the basically official CPI data, right? Which is like local frequency. This is more like based on our everyday discussions and maybe coffee price, egg price, right? So S means it could be like, because every month we have 30 days, right? So you can do every day you have proxy. On the other hand, you can argue this is too noisy, right? You can aggregate, for example, every month you can divide into 4 weeks. First week, second week, third week, and fourth week, right? So S could be 4. You have 4 numbers. And so you're trying to leverage the correlation between the two sources. A simple, this is a picture I'm showing you, right? So once you do the fitting, you realize actually this is from official data. This is LLM-generated proxies. And if you look at residuals, they are indeed they're indeed correlated, meaning that this is something you can leverage for more accurate forecasting. So I would say this is the most important empirical plot for motivating the methodology. Yeah.
What is the first, middle versus last?
Oh, this is basically, okay. This is like every month you divide into 3 periods, like first 10 days, second 10 days, and last 10 days. Yeah. So So essentially, here's essentially the AI generated signal. This is official signal. Of course, I explained how to do modeling, right? Then you look at the residuals, and turns out the pairs of residuals, they are indeed correlated. Yeah.
Well, there's a huge difference in scale, if I understand that. No? Like one was from 0 to 0.8, and one was from 0 to
I know visualization.
So
yeah, visualization is not perfect, right? Yeah. So yeah.
Like, how correct is that? It's like really like this.
But also, I mean, you have, yeah, it's hard to tell what, like, so perfect correlation on this would be like would be a lower left to upper right line, right?
Yes, right. Because I'm teaching the into stats for my students, right? Let me clarify. This is not the best plot to show actual correlation, because this is only give you the qualitative, but not actually say how strong, because they're not same same scale, right? I agree.
If you took off those lines, it would just kind of look like a random noise, wouldn't it?
Yes, actually. So let me see. I think the scale here is a little bit confusing, but I don't have the plots here. In the paper, actually, we reported the correlation. Actually, it's some correlations, not all correlations. Some correlations are actually stronger. For example, could be up to 0.2. Yeah, meaning that indeed there's coupling dependency. Yeah, right. I would say yeah.
Sorry, can you make the slides full screen? Because I can only read the
Oh, it's not full screen. Oh,
no,
I see.
It's like.
I didn't realize.
I only see it. I only read it because I'm very close.
Command L.
So do you actually have 63 slides?
Oh, then now it's full screen. Okay, I see. Yeah.
We should know that we have like 7 minutes left.
Okay, yes. I'll try to wrap up like in okay. Great. So this plus only give you a verification that there is some sort of dependency. I'm not giving you the official numbers here. Yeah. But in paper, we have the actual numbers. So meaning that the two sources are correlated even after you take the residuals. So this is actually a little bit explanation, say how it works. So essentially, since the two error terms are correlated, so you can do the learning based on a surrogate model, and then you can try to basically calculate residuals, right? You can feed residual into the first benchmark model. This is the equivalent, meaning that it's LLM component coming from this part. Okay, so the advantage of the whole system here is we're not trying to link the parameters between the two models, but we are trying to borrow from the correlation in the noise terms, meaning that the system is robust, because any model we wrote down for the LLM part could be wrong. It's only a reflection on the reality, right? So if you do the noise correlation, actually it's more robust. So actually we have extensive studies to show that. So here basically one simple calculation showing though that, so this is a correlation rule, right? Imagine if the two have correlation 0.5, what is the efficiency gain? So 0.5 squared will be a quarter, right? So 1 minus 1, 1 over 1 minus a quarter, roughly speaking, you have the 33% increase in terms of efficiency gain, meaning that your interval is going to become tighter. This is the first message. Yes. So essentially our algorithm called LLM-Powered time series predictive inference, LLM-TS method. So I'm going to skip the technical part, and we can show that we have the prediction intervals with theoretical justifications and different ways to calculate. And next, let me say about the data part, right? So in the paper, we have multiple applications, but during the talk, I'm going to focus on the Chinese CPI prediction problem. So this is the social media site I mentioned, right? The Weibo website. Actually, the huge amount of users every month. For example, like as of March of 24, about 600 million monthly active users. And we look at the 5-year data from 2019 to 2023. And by the way, it's a huge amount of text information. It's highly noisy because it could be ads, promotions, and also unrelated topics. Outside of, for example, like
what are the keywords then? You look like price, inflation. What are the keywords?
Yeah, because we're trying to capture inflation, right? Essentially, I don't have it here. Maybe it's some Oh, yeah. It's actually we extract 25 keywords relate to, for example, the prices, and also in China, because people value the home basically be home price and home buying, all these words, yeah, that can capture the.
You have the keywords in the paper?
Yes, right. Yeah.
Because I mean, I guess if you say price, it could be many things.
Oh, that's very true. Yeah.
There's
The price of this product or whatever.
Yeah, that's true, right? So because this is actually a little bit subtle with language, right? Because price is so general, right? And so in the paper for this one, actually, we designed 25 keywords, trying to capture this kind of movement. Yeah.
I just wanted to see the keywords.
Oh,
move on. It's okay. It's okay. You can go on.
Yes, right. Unfortunately, I did not put it on the slides, right? But if you go to the archive version, actually in the basically in section 2, you can find a list of keywords with translations. Yeah. That's why we extract about 120 million posts based on this 25 keywords. Yeah. If you did not do filtering, of course, there's a lot more posts. Yeah. So how do we use LLM for the signal construction? So there's 3 steps. First step is actually we use a chain of thought prompting, trying to get some labels of the posts, right? Because this is more like trying to ask LLM to score the inflation. For example, suppose you write a piece of post online, right? And you feed into GPT and you want to get a number. 1 means absolute inflation, 0 means absolute deflation, right? But thing is, we don't have label data, right? So what we did is we took a random sample of 20,000 posts, and initially we worked with GPT, say, what do you think of the inflation level, right? Between 0 and 1, and then we did a human verification and evaluation, trying to make sure the labels will be meaningful. So that's how we created basically the annotations by working with GPT. And once we have the high quality labels to start with, which is a small set of labels, we trained 3 specialized BERT models for different purposes. Because for text information, it could be, for example, could purely say, do you want to buy a car, right? It's like purely like an advertisement. Or it could be, for example, about a fashion or sports, right? Which has nothing to do with inflation. If it's in inflation, we want to have BERT model give you a continuous number. So then we try, after train the model, fine-tune the model, we apply this the models to the actual 120 million posts to get all the information here. So here's one simple example, right? If post actually about an ad, then of course we should not upload anything, right? So it's not inflation. Or is the text information is not an ad, but could be lifestyle. Of course, we don't output a score. If it's not an ad, not like in the other category, it's about inflation, we should have a number like 0.8. It's strong indication of the inflation, right? So for the 3 specialized fine-tuned BERT models, actually we look at the AUC curves. It's pretty good accuracy for different purposes, classification and also final prediction. In the end, we're able to retain about 5% of the posts, meaning majority has nothing to do with inflation, around 5.8 million posts.
So those experiments, how many? What was your test and your training set for that experiment? So that AUC is over how many examples? How many?
You mean this one?
Yeah. So you did this experiment with 20,000 or?
For 20,000, okay, this is different steps, right? Before you can run this one, you have to create high quality labels, right?
Yes.
That's why you took a sample of 20,000 observations and trying to get labels, and then
you train the BERT models, and then you apply the BERT models to do this.
Yeah.
How big was that training set or that test set that you applied this for?
Oh,
you have to have labels that you have to know if there's an advertisement or a category or a CPI. I'm just saying, how big was this test?
Okay. A very good question, right? For this one, actually, because label was created by by GPT, right? By working with the interactions. Essentially, we're trying to fine-tune BERT model, trying to mimic what GPT was doing. Because this is like a black box decision-making process, right? Yeah. So essentially, this one is based on it's based on you're right. Yeah. So this one is actually you train the model and you trying to make sure it's actually trying to mimic the actual GPT process, right? This is actually based on the label data, because otherwise you don't have the labels to evaluate here.
I just want to assess how those 5.8 million influential variables, how pure is that group? I mean, like, you assume that it's like 90% accurate, so there will be. That's what you think they were inflation relevant, but there may still be lots of other things that are not.
Oh, okay, I see. I agree. So it's this number is calculated based on the 20K because you have labels, right? And based on this one, I mean, overall, it's reliable, and in the end, they get this one right. But on the other hand, because GPT is not perfect, right? Number one, to start with. Number two, the trained model may not be perfect, right? Yeah. So So I mean that, yeah. In the end, essentially for this one, actually. Well, you can think of this as like a raw outputs. It may not be perfect, but actually it might give you some good information about what happened in inflation.
Move on, because I think we're running out of time.
Oh, sorry. Yeah.
So you have this 5.8, and then okay.
Yeah. So essentially meaning that for every day, for every post, you can get a score if it's inflation related. 1 means absolute inflation, 0 means absolute deflation, right? So all of us can vote, right? For a single day, you look at the posts and get the average. That's why for every day we can look at the so-called up scores and down scores. Up being your score is over 0.5, meaning that it's going up, otherwise going down, right? You do see lots of basically variations. And for example, during the beginning of COVID, actually more discussion about inflation. On the other hand, later on, the more discussion about inflation down, right? So unfortunately, I don't have time to go through specifics, but hopefully get a feel about how basically the LLM turned the data, the text into the signals. This time is up. I'm going to quickly show maybe some quick tables, right? How useful the technique would be. So this is actually, we use ARX, the benchmark, because we're taking ratio. Whenever number is lower than 1, we're beating the benchmark. So for example, if you think about the LDA, this embedding, right, or BERT embeddings, if you do this embedding directly, sometimes can hurt you. It's worse than embedded baseline. On the other hand, if you use our joint residual modeling idea, miraculously, even if it's better to start with, like this one, we can turn highly noisy information into useful tool for inference, meaning that here's actually have big improvement. Our inference actually is more accurate. Its prediction error is 0.9 and 0.8 for the LDA models. So whenever it's below 1, meaning that it's more accurate, yes.
So I can see with the LLM plus BERT, it's still sometimes over 1, but with LDA, it's never over 1.
Yeah.
Any sense on why?
Yeah, people actually, I give several talks about this one. My interpretation is, on one hand, BERT is still flexible, right? On the other hand, any embedding you get from BERT, which is high dimensional, 768 dimensional, right? It could be noisy to start with. So I don't have simple explanation, but nature of AI. But the point is, if you ask our idea, even it's noisy to start with. So now it's actually beating the benchmark, yeah.
So what are the 8, 9, 10?
Yeah, this is horizon. It's, for example, like
8 days away.
Yes, right. 8 days away or 8 months ahead, right? Yeah. For CPI, will be like months. Yeah.
You would expect it to get steadily higher, though, right?
Worse, no? Because yeah, 15
right.
months is harder than 8 months.
Yes, right.
And yet there's a weird, like at 12 months for a few of these things, it drops suddenly.
Yeah, this is interesting. Because the series actually is also highly variable, so it's highly random, right?
It's also highly variable.
Yeah. So which means the number you see here, yeah. So actually, yeah. So overall, actually, it should be on the this trend, right? Yeah. That's why basically, if you look at the average number, actually is more stable, right? Yeah. Yeah, you take average across different horizons. So here, so I think to us, essentially, interesting message is. Like LD is good to start with because it's more interpretable. For using our idea, it's more accurate. But for the BERT, actually, the embedding itself actually noisy, but we can turn this into something that's useful. Yeah. Next table actually is interesting because we can try to predict the inflation for tomorrow, right? On the other hand, as the easier question would be whether it will go up or go down tomorrow, right? So it's basically a binary prediction problem. So which means trying to predict a sign up or down. actually for that problem, indeed error can be much lower. For example, LLM plus LDA method can be 0.2. It's more like a 80% reduction compared to the benchmark method. Yeah.
So what's the time horizon? Is it months or is it days? What is it exactly?
Oh, this one. So let me see. Because
No,
this
days
is because
would be easier than
because the
months.
CPI is actually
It's daily or
let me see. No, CPI here is actually the data is monthly data.
monthly?
Yeah, right. Because only like you have the gold data actually is what government publish at the end of every month. Yeah. Oh, by the way, for this one can apply to any time series problem. For example, if you look at say unemployment rate or other problems, right? You have more high frequency data, could be day by day. Yeah.
But the better method is LDA, no? Lower is better. So LDA
lower is better, right? Because you're taking
LLM
ratio compared to a benchmark, meaning that you take a ratio. If smaller, should be less than 1. Yeah. And also we did a coverage. So again, I'm not going to read off the numbers. It's too messy. But the message is, if you use, for example, LLM idea in this basically in our project, actually we can see that our coverage is close to nominal level, like 95%. But on the other hand, is shorter because if you look at length, it's actually it's big reduction. And also we applied, say, COVID-19 because COVID-19, you can think of as a natural like a shock to the economy, right? Because you can think of the following: if you develop a like system for prediction, you want to make sure the system is stable, right? So we treat COVID-19 as a shock. We want to see what happens, what behavior of this method, before COVID or during COVID, after COVID. Again, because time limit, I'm going to read off the main message, meaning that the results, across different regimes of this time series settings, actually highly robust. So, for example, if you look at the prediction errors, this is results for during COVID. So essentially, this is LLM LDA method is around 0.3, and for sign error is 0.1. And if you apply the same method to after COVID, it's still consistently lower, but so which means the method actually more robust across different dynamic scenarios. And the final word is the problem. The algorithm not limited to CPI prediction. Actually, as long as you have time series target, for example, could be GDP or unemployment, you can apply this idea. So the central piece is you have basically 2 data words. One is high quality data, but it's more scarce. For example, comes as like a lower frequency, right? Monthly or whatever, right? On the other hand, you have a bunch of quite abundant noisy text information, which is high frequency. You can blend the 2 into the same framework. And the key idea is use LLM to provide the construct surrogates and to try to couple the 2 error terms in the 2 models. And in the paper, by the way, we did quite a major revision recently. We did the CPI for both US and China. The results very consistent. And also we look at quite a number of like over 20 macro indicators in US. The findings are similar, meaning that the methodology actually is broader than just looking at the CPI. To sum up, actually, in this project, I think over time. So we're trying to understand how to fuse online text with the interpretable time series models. And our framework actually gives us basically a better, lower forecasting error in terms of like direction output. Actually, the forecasting actually is also improved. So our inference method gives us a tighter coverage. And we also look at the robust testing given under the COVID-19 regime shift. So here's basically the papers I mentioned. So I was focused on this first paper, the LLM-powered predictive inference with online text time series. And also, this is something I mentioned at the beginning of my talk. I really want to talk to folks here because this is the ISI, right? So this is about how to evaluate quality of summaries, right? So both papers can be found online. And thank you all for your attention.
I guess we can wait around for questions, but I think we can stop the recording.
Oh, sure. Yeah. Thank you.
So questions.
question on if we want to apply this, and I think you said if we have a lot of highly available noisy data, and if we have like less frequent high quality data,
Right.
do we still have to check? I mean, I guess following your method, we have to check whether the noise is correlated between the two sources, right?
That's very true, because that's why you see the reduction in the forecasting error. If the two there, okay. So people often ask the questions, right? If I use LLM for prediction, can I just throw in whatever LLM outputs or BERT embedding to do prediction, right? Oftentimes, sometimes can hurt you. So which means that if there's not much correlation, it can give you information. But if you use the error coupling idea, right? Even it's noisy, it's not like correlated, it won't hurt you. I mean that it's still quite stable, but not like you're doing much worse. Yeah.
I translated the figure 8, which was the, I think like a tweet in Mandarin to English.
Yeah.
And it's like a retweet of a channel called Financial Commentary.
Yeah.
And it has like information like price rises by 12 yuan per gram in one day, and like some human level like meta information about the economy. And the only thing that's like a extra information that's by giving that to LLM is like some kind of like using human knowledge for predicting the CPI.
Oh, actually, it's interesting because we did analysis, and in the end, we're trying to validate whether the results are interesting, right? That's why I produced the result like this one. But in our framework, we did not look at metadata. For example, if you put something, right, you might retweet or people cite you, right? So essentially, we only look at the actual post. And that's very basic text information. But the meta information could be additional information you can leverage for forecasting. Yeah.
But like I'm saying, so like I can ask this question two different ways. One way is like as a baseline, you could have only look at these like financial commentary level accounts which express their reaction to economy.
Yeah.
And these are like real humans who are writing about the economy.
Yeah.
And then if let's say you have an LLM that you feed these information to them and then ask about CPI, that LLM would have a better guess, like and would have been a more powerful baseline, I would say. This is one way. The other concern I have is that what if these information from these data points get into your models and make it like a I don't know. I feel like it's like a cheating somehow to like give it to this information.
Yes, right. So actually, you're mentioning that you're focused on a subset of text, right? For example, if you know that the data source is like a credible, high quality, in principle can help you, right? But on the other hand, if you fit into large language model tools, right, the output themselves are noisy, so it's random, which means you have no control. So which means because this is like a black box model, right? Output, right? So any basically the labeling, scoring, and output from this kind of tools in the end could be noisy, and that's why it may help. Yeah, but yeah, it's hard to tell in the end in terms of final prediction. Yeah.
Thank you.
Yeah. Thank you.